Is the screen visible?
Yes, sir.
Yes. So I just gave you a mail regarding a little bit of background on MLE to refresh because we will be needing it. So I will cover as a kind of a recap in between. So essentially, I mean, if you just refresh your Bayesian net kind of structure where we are trying to learn certain probability distributions. For example, suppose an arbitrary Bayesian net, suppose there is a flu. This is node for allergy. And suppose your sinus problem depends on flu and allergy. And as an outcome of the sinus, you get a headache or sometimes you get a running nose. So this is a typical Bayesian network structure that we usually see, that we have a dependence graph or rather a directed acyclic graph which presents the dependencies of certain event with respect to the previous. Now, it would be absolutely great if we also have the conditional probability distribution table for f equal to 1, 0 here. For example, the table that relates for s equal to 1, f equal to 1, a equal to 1, f equal to 0, a equal to 1, all that. So we know that these are conditional probability distribution table, which is associated with each of these nodes. If it is given, then our job is pretty much simplified to get the joint distribution table. So Bayesian net with respect to each node having a conditional probability distribution is equivalent to get the full joint distribution structure, because now if I want to seek what is the value of capital F taking the value F, capital A taking the value A, similarly S, H and N. By this, I just mean that capital F will take the value F. By this, I mean the capital A will take the value A. So you can see this is a probability entry of a joint distribution table where the joint distribution table values are small f, A, S, H and N for these variables. And as you know, if you are given the Bayesian net structure, you can easily decompose it by a simple formula with respect to the conditional dependence, that S is dependent on FA, probability of H given S into probability of N given S. Now, this is basically what we are trying to compute here is the joint probability distribution table. Now, either Bayesian net and the CPD both are given, then this we can easily compute. Or we can have this kind of a table upfront in our hand, then obviously the Bayesian net structure and the conditional dependency we can get into it. So these two are, we could say that are interrelated. Any one of them is given, our job is very much simplified. Now, as per the learning perspective, you could think of these problems could be of four, it could manifest into fourfold. So as we know that we are given with a Bayesian net structure, and let's say you have a data set which contains the values of f, a, s, h, n and the probability. So this kind of a table is given to you. Now you can easily understand that why such kind of a consideration we are trying to think is that sometimes, let's say medical data, we know the dependency that sinusoid is caused by flu, sinusoids can be caused by allergy. So we have the typical dependency graph structure in our hand. However, we may not have these conditional dependencies associated with each table directly. We may have for some of them, we may not have for all of them. Rather, from the field, we can have collected some kind of a data with certain values of probabilities, and we have these data. Now, as you could see that collecting a joint probability distribution table fully, that is fully informed joint probability distribution table, may not be feasible because of the number of attributes. Now, the problem is this this way, the four-way, that suppose Bayesian net structure is given to you and this partial data set, but fully observable. The data points that you have is fully observable. We are saying this is as fully observable, meaning that there is every entry. So suppose these I have very few number of them. Suppose I have n number of them, but all of them are complete. That means fully observable. So I am given with the Bayesian net structure, that is a dependency in the scenario, and some data. It may not be complete set of joint probability distribution, but whatever is given is observable. So other option is that you are given with Bayesian net, but there are some position of the data that you could not found from the field study. That I do not know whether sinusoid and nose running together data with respect to he has a headache, he doesn't have an allergy, and he has this flu. I didn't get this data. It may also be it may also so happen. So this kind of data we call it as a partially observable. Right? So under these circumstances where the joint probability distribution table is not fully enlisted, finding out this CPDT, that is conditional probability distribution table with respect to every node, is ultimately a learning problem. Agreed?
Yes, sir.
Yes, sir.
So therefore, we are trying to learn such kind of a conditional probability distribution values. For example, what is the probability of S given some value of F and A? These things we are trying to learn from a partial set of joint distribution table, fully observable is problem 1. Given Bayesian net structure, if it is partially observable, what we will do is problem 2. Bayesian net structure we need to learn from a fully observable data is problem 3. Bayesian net structure also fully not known. Data is also fully partially observable. That is the most difficult problem. So we will try to tackle one by one, and we will see that one kind of algorithm particularly fits for many of these. So first problem that we are trying to mention is I have a Bayesian net which is known, but plus I have a fully observed joint probability distribution table. Fully observed, do not get do not misclassify as fully observed, meaning that full set of joint probability distribution entries are given. Fully observed means there are some entries, but everything is complete. There is no vacant places here. So in that case, what we will do, our challenge is, that is our challenge. Our challenge is to learn conditional probability distribution table. Suppose we would like to learn for, let's say, this example, sinus. This is not known to us in this problem. Let's say I want to know the conditional probability distribution table of sinusoids, which means I want to learn theta. Let's say I have a sinus or not, S equal to 1, given I have a fever value of I and I have an allergy value of G. So this table is not known. For S equal to 1 for different value, I want to know this conditional probability distribution table here, looking at this data that I have and the Bayesian net structure that I have. Okay, problem clear? What we are trying to address? First problem.
Yes, so there is a small question.
Yes, sir.
Yeah.
Like in the case of you are telling fully observed joint probability distribution, we have 2 to the power n entries.
No,
like for
no. You have less entries, but whatever entries you have is complete. Okay. Suppose you have collected data such that whichever probability you get it, you know what is the N, H, S, A, and F value. Some case it may happen that you get a probability value, but you cannot relate the headache with nose running and sinusoids and all. So these you do not know what is the value. If it is 0, what is it? If it is 1, you do not know. But you have got the data that whoever has the fever, not the allergy and the headache, this many probability of them.
Okay.
That is partially observed.
We don't have the vacant entries, and we don't even have the full 2 to the power n entries.
Yes,
whatever we have,
do not have the full joint probability distribution table. That's why we are going for a learning problem. I mean, the goal of learning problem is that, see, if you have this one or this one fully, you are done. You can do anything. So the goal of learning problem is that you will have partial this one.
Okay.
That is field collected. And even if partial this one could be, I mean partial in terms of the size less than 2 to the power n, as you are saying, and partial in terms of observation, it could also happen. That I may not get all the possible probabilities with respect to each of these values, but I collected that somebody has fever, not allergy and headache. I got 60% populations on them. They have sinusoids or nose, they have not reported it.
Okay, so we will learn these vacant places and other entries. Which
That's the
we are
second
not
problem I will
other
tell you.
than
The first problem, Bayesian net known, joint probability distribution table not fully given, but the data are fully observed.
Okay,
I would like to learn the sinusoids conditional probability distribution. For as an example, you can learn anything. I have taken this one, so that I would like to learn this.
Okay, sir.
Right? This is the first problem. Now, as you can see, if you now try to remember a little bit from our MLE discussion, let me just refresh our MLE discussion, maximum likelihood estimation. So remember coin flip example. So what does maximum likelihood estimation does? It tries to find out a particular probability that maximizes the likelihood of data given theta. That's what it tries to do. Which means that if you remember our coin flip problem, you have a 0, 0. I mean, 0 means tail. Rather, I write it that way. It will be easier. So suppose I get a tail, I get head, tail, head, tail, like that. Now, what we did is that suppose I get alpha 1 number of heads and alpha 2 number of tails. So this data can be looked upon as the probability of this data could be looked upon is theta is the probability of number of heads and 1 minus theta is the probability of number of tails, and we are getting alpha 2 of them. And we are trying to maximize this, remember the log of this differentiating, and finally we are getting this one as when we maximize this part with respect to the which theta will maximize it, we get it as this one, remember? Right? That's our maximum likelihood estimation.
Yes, sir.
So which means that given a data, if I have to follow up with a theta value that maximizes the likelihood of the data probability, then this is the estimate of the probability, even though I do not have all data in my hand. So this is one of our weapon to use in this algorithm, as you can understand easily that we do not have all data in our hand. So therefore, one of the ways, since we are trying to learn, let's say this particular thing. So one of the way is to use maximum likelihood, and obviously you can see I am writing this as small s equal to 1. I'm indicating it as and if I'm as this one. So you can see easily which will be, suppose I have k number of examples. So for each example, which of the examples satisfies the kth f value is I, the kth a value is j, and the kth s value is 1, divided by, look at this formula, I'm just applying it. Kth f value is I and kth a value is j. That's directly from the maximum likelihood estimation. Right? That means what? That means I have a table, joint probability distribution table. I will just count this F, A, and S are my columns that are of interest. I will try to count which of the columns. So delta is a binary function. If the column has F value as I, A value as J, and S value as 1, that is counted as 1. Other columns doesn't match these three values are counted as 0. So all those columns which are these three values matching, I will count them. Divided by all those columns where my A's and A's and F's are matching. I do not care about S because I'm trying with respect to Bayes theorem and all that. I derived this one, right? So this will be through maximum probability likelihood, the conditional probability distribution, learned value of conditional probability distribution table for S equal to 1 given F and A are respectively I and J. Agreed? Okay.
Yes, sir. Yes.
So therefore, I mean, you can just dig down. I'm just pushing it a little bit more so that you could derive the operation. So what is this in this case, as we derived in terms of the coin flipping, it is nothing. But for all the examples, it's a probability of Fk, Ak, Sk, Hk and Nk. Simple as we did a multiplication of probabilities of heads and tails. Here there are many combinations of such. So we take a multiplication. So effectively what you need to do, you need to have a d theta of Sij and need to maximize the log likelihood, log of probability of data given theta, by which we from here we derive this one. Similarly, if you go on doing this one, you automatically will see that this, depending on the Bayesian net, because Bayesian net is known to us, is nothing but the summation of k log fk plus log ak plus log sk given fk comma ak plus log hk given sk plus log nk given sk. Why? Because this is a multiplication. I take a log and that will go as a sum of the whole thing. This thing, as I know each of the joint probability distributions from the Bayesian network, I can write it in this way. So this way I can do. So when you do a d theta of that, you can see that only this parameters is of our importance. The rest will be cancelled when you take a d theta. So if this is effectively, it will be d theta s given ij of the log of sk, I mean log of not this one, log of probability values, because I missed the probability term, the probability of sk given fk comma ik. And now when you go with the same approach as we did in MLE estimation, just do with that, you will land up with this formula that we just said. I mean, this is just an illustration of how we get it here. It's the same illustration as we do it for the coin flipping. Agreed? So it's a pretty simple problem. It's a fully observed set. Now we need to have only within this realm of the data that we get in, I need to compute the sum of whose satisfies all of them divided by according to Bayes' theorem that satisfies these two of them. And I get a maximum likelihood, and it matches with our this kind of a raw estimation matches with our theory, because our theory says this way. We have seen for the coin flip. I leave it to you to prove it from here. Clear? First problem.
Yes, sir.
Moving on. So next, as you can understand, what I will do, Bayesian net should be known, data should be partially observable. So problem 2.
Excuse me, sir.
Yeah.
Sir, could you show the example for previous problem? One example.
Yeah, just make an example in this table. You make an arbitrary set of, let's say, 10 columns by yourself, 1 0 1 1 0 and all that. Okay, right?
Yes, sir.
Then just count for f, let's say for f I equal to 1 and j equal to 0 and if s equal to 1, how many of them? And count how many of them are for f equal to 1 and a equal to 0 only. You just divide that. Get it?
Okay. Sir, this delta will not be the probability or the count of the this 1
No,
and
but
0.
you only have this data to make the probability. So this is an estimation of the probability.
Okay.
It's a learning estimation of the probability. It's an estimate.
Okay. It will
So
give
how we
the
get
data.
it? How we get it? We get it through probability equations and deriving through which maximizes this. Ultimately, it comes this way, because in coin flip you saw it is just the number of alphas divided by the number of alphas plus number of alpha 2s.
Yes, sir.
So we
But sir,
derived it that way finally.
the final value of probability, how we are going to get? We are going to put the theta for that.
So you are getting a probability value. This is a probability
Yeah,
estimate.
okay. Okay, sir.
This estimate will come from the number of rows that satisfies the numerator divided by the number of rows that satisfies the denominator. That's the probability value.
Yes.
Obviously, the number of rows satisfies the denominator will be more or equal to this one, right? So it's
Yes.
a value between 0 to 1.
Okay.
Okay.
Yes.
So the next thing, as you easily can predict, that I have Bayes net given plus I have a partially observed joint probability distribution term. So which means So suppose, let us take x1, x2, x3, y something, which means I was given 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, and then suddenly 0, 0, 1, I do not know, 1, 0, 0, I do not know. So this is what I mean by the partial thing. Now you can see there could be 2 to the power 4 number of possibilities, but only I give you 5 in the JPDT. That is our old fashioned learning part. That from here we have to learn, but additionally here the constant comes that I do not know something. Okay. Good. Now here, as you can see that what would be our philosophy? Let us first try to think the common sense. So this could be either 1 or this could be 0, right? You do not know. Therefore, when I compute the maximum likelihood as I did in the previous case, I would take the contribution of the column multiplied with expected value of that column B1, and also I will take the contribution when the expected value of that column is 0. That's a fair enough deal, right? If we do that. So here you see, since this is 1, so therefore the contribution of this column when y equal to 1 is cent%. When y equal to 0 is 0%, because I know this y has y equal to 1. This column has y equal to 0. That means the contribution of this column when y equal to 0 will be cent, and the contribution of this column when y equal to 1 will be 0, because y equal to 1 is not occurring. Here I do not know what occurs here. Therefore, I will take the contribution as if it is weighted by the expected value of this particular entry to be 1, or it is weighted by the expected value of this particular entry to be 0. Right? Fair enough? We could do that.
So for this, we are assuming that probability distribution of y will be given, right? To calculate expectation.
So here you are saying that no. See, there are so just wait a bit. I mean, let me complete what I wanted to say. If I have this, then I could do that, right?
Yes, sir.
Okay. Now see the point. What I will do. So therefore, here the problem is that if I wish to compute for all the examples, Fk, Ak, Sk, Hk, Nk, the problem is that I have, let's say, for example, I have this as partially observed. So this was just an illustration, but coming back to our this flu, allergy, sinusoid, headache, running nose problem, Bayesian net, this is given to us, but this is not observed. So we classify it as the observable things are F, A, H, and N, and unobservable set is S. Here, the unobservable set was Y in this example. Now, the problem is that now we cannot directly do the maximum likelihood estimation because these columns are of problematic nature. So, in those cases, what we will do in 2 steps, and obviously we have to go by iterations. So, step number 1, what it will try to do, it will try to fix the expectation values or the expectations. That is, it will try to first find out the expected value of Z given X and a prior theta that your friend was telling, and a prior theta value for all. Suppose that is given to us, then we can compute these expectations. Yes or no?
Yes,
With
sir.
respect to some prior probability value, if it is given to us, then we could compute this expected value whether it is y is 1 or expected value y is 0 for everything. So that means for the unobserved variables, we can calculate this expectation. The second step would be now our traditional thing to find out from the argmax of all possible thetas. However, here instead of directly computing the log likelihood to maximize with respect to the variables we have, we are trying to compute the expected log likelihood to be maximized. Fair deal? Let me repeat what we are trying to see. See here, you can see the philosophy. Now my philosophy is that this particular entry I need to contribute with respect to thinking this as 1 or thinking this as 0. The more the probability of it to be 1, the more contributions it will make when I think it as 1 and vice versa. Therefore, I need to compute for the unknown entries the expectation and the contribution of the likelihood, or rather we call it as a log likelihood because for the sake of computationality, we do it as a log. Not the log likelihood, but now we have an expected log likelihood. Because I do not have the full data. I have a partially observed data. I need to compute the expected value of that partial entry and make it. So what we will do, we will start by assuming an arbitrary theta value. It doesn't matter what do you assume. Let's say 0.5 for all. Maybe, or maybe customize 0.6 for someone, 0.4 for someone and all. Then compute this step, then try to maximize this. Then go again with the updated value to do this. Then find the second updated value from here. Go again with the updated value with this. Go on doing this. Right? Until we converge these two as we stop our iterations in our normal programming, until we converge that we are not changing much.
So let's execute the first one, right?
First, you will execute the first one assuming arbitrary theta value. It doesn't matter. You will compute the expectation of the unobserved variable value, that is this y equal to 1, given that you are some observed value and some probability of whatever you want. But next time the probability values for each of them will be updated from this update step and will feed back. Next time again in this way we go on. So if you understand this philosophy, and so this algorithm, as you can easily understand, it is expectation maximization, or in short we call it as EM algorithm. Okay, so now I would like to just draw with some of the mathematical notions of it. So what we do is that step 1 is nothing but calculate the expectation, that is the probability of unobserved variable given x theta, and calculate the expectation of that. And in the second step, when you maximize the argmax of new theta value with respect to q this given theta. And whereas this thing is nothing but the second thing I wrote, expectation of z given x comma theta log of probability x comma z given theta. This one, I just wrote this one. So now let us try to see with the kind of a synthetic example what we will do in terms of Bayesian network. Suppose again here we would like to learn the value of theta s given ij. So first, since some of the s values are not there, it will be my expectation step will be first. So how do we compute the expected value of s being 1? How do you compute the expected value of sk being 1? Suppose the kth row has a missing data for s. So this is nothing but, so if you remember how do we compute this one, is again we will try to figure out this as a probability of sk to be 1 given my fk, ak, hk and nk and theta divided by probability of sk equal to 1 given fk, ak, hk, nk, theta plus probability of Sk equal to 0, same thing, Fk to Nk theta. Which means that in the first step, suppose I assume an arbitrary theta, which means this gets diluted into theta of Fk into theta of Ak into theta of Sk equal to 1 given Fk and Ak into theta of Hk given Sk into theta of Nk given Sk. This one, the top one. Similarly, the bottom one, you can easily understand this part will be there, plus everything will be there from this part except this one will be Sk equal to 0. I am not writing the whole things. Get it? So at the first step, when you try to compute the expected value of that Sk to be 1, it is nothing but prior assumed probability values that you have for the theta, and you can compute this one at the first iteration of the first step, that is iteration 1, first step. Get it?
Yes, sir.
So I write it as an expected value of Sk to be 1. Since Sk can take 1 and 0 value, I am assuming. So I write it just as Sk. Okay. Now, once you do that, just let us look at this expression, the maximum likelihood when I know where Sk is 1. It is not partially observed, just in the previous case. However, here, as you can understand, instead of this one, I have an expected value of Sk for the unknown parts and the value of Sk to be 1 for the known parts. Yes or no? Right? For the unknown parts, I will use this value. And for the known parts, I will use whether it is 1 or 0, whatever is there. So therefore,
Yes, sir.
let us go with the second step of the iteration 1. Then in the second step of the iteration 1, we are trying to figure out this updation. This I will update from the maximum likelihood delta Fk equal to I, Ak equal to J, expected value of Sk divided by all the examples where Fk equal to I and Ak equal to J. Now see here, for the known Sk columns to be 1, this value is 1. For others, that means for the Sk to be you don't know, previous step has give you some expected value of Sk. You will use that in that summation. Clear?
Yes.
Sir, can you go on the previous page?
Can I repeat, or?
Sir, can you please move to the previous page once?
Yes.
Sir, where are we using the theta over here? Like the already given condition.
Here.
Theta is S given.
Yeah, everywhere here. See, to calculate the expected value of Sk to be 1.
Okay.
See, expected value of Sk to be 1, expected value. That means you need to know this Bayesian, by Bayesian rule. And we are computing the previous iteration theta. So initially it was a predefined theta. In the later case, when I repeat once again, iteration 2, step 1, then I will use all these theta values for S given Ij. So S given Ij theta value is the unknown part for me because I do not know this part. The rest I know, right? I will use this to compute again for the second
We
step.
are just updating this value, like S given Ij,
Yeah.
right?
Yeah, this
Other
is the
one
first
will be
iteration.
constant, right?
Yeah, and also for the Sk equal to 0 as well. For Sk equal to 1 and Sk equal to 0, because the conditional probability distribution table you want to learn now.
Okay, sir.
Okay, so then again we will go by this way until we converge. But here the only difficulty is that, as you can see, that if you look very closely to this problem is an NP-hard problem to optimally find the solution, whereas you can easily go to a local maximum. Since we are maximizing the expectation, you will get a local maximum, and you will be stopping here. Okay, you can easily understand because it's an iteration wise. I am first freezing the theta, using the theta to freeze the expectation, then coming again freezing the theta, using it to. It is not a globally we are trying to do something. We are trying it stepwise. So obviously the convergence as we did in case of stochastic gradient. So if we do one by one and try to move and try to find my local minima, we can stuck in a local minima rather than going to global minima. Here also the expectation maximization may stuck into a local maximum. Okay, but what people do usually, they try to start with different theta initiations. That sometimes help them to get rid of a very shallow local maxima rather than to reach between an average higher maximum. You can easily understand why I am telling this because initiation matters to go into maximization problems. Okay. So this is the second case, but let us also a little bit think a bit more towards the Bayes classifier side of this case. See, in the Bayes classifier, it's a Bayesian net. However, the Bayesian net has a typical structure, meaning that it is a monolithic entry of from y dependency of x with y, and nobody of these are dependent because we assume every input to be conditionally independent. Yes or no? Remember, right? That is the Bayesian net.
Yes, sir.
Now in Bayesian net, for example, I have some y's with respect to x1s to xn's. And let's say some y's are known and some y's are unknown. So you can apply the same algorithm there. So there in the first step, when you compute the expected value of y given x1 to xn, then it is, let's say, yk equal to 1. Then it is nothing but you know that what we do it probability of yk equal to 1 into, since the conditional independence is there with respect to every xi's, so xi k given yk equal to 1 divided by the Bayesian theorem says for sum equal to j equal to 0 to 1. I am assuming 0, 1, 2 possibilities. Probability of yk equal to 1 into this part will come here. The simple thing. I mean, I'm just converting it to Bayesian Bayes classifier, Bayesian classifiers. I mean, just for as an example. And again, in the maximization step, where you need to maximize the value, let's say of xi taking a value j given y equal to m, xi taking a value j given y equal to m. If you need to maximize, the same Bayes theorem will apply. Just finally, what you will get, I'm just writing it. x1 k up to xn k delta of xi k becoming j divided by, as you can understand, it will be the full summation with respect to probability of yk equal to m given x1 to xn case. So basically the same thing in terms of Bayesian probability rule, where we can also do this conditional independence of the lower nodes. So typically these kind of things are very much applied in Bayesian classification as well, because most of the time we do not get fully observed data. Okay. So this is two parts. The other two parts is a typical, suppose we are Bayesian net. So the problem 3 in our case was Bayesian net not given plus fully observed data. So this is a typically difficult part, which you would say. So there is an algorithm called Chow-Lin algorithm, which uses KL divergence. We are not covering it in this part of the syllabus, but if you are interested and need somewhere in your practical life, so what this does is that this used to compute a KL divergence and try to find out a tree structure Bayesian network. So it will not be kind of a directed acyclic graph, but a tree structure Bayesian network it finds out by this Chow-Lin algorithm. We are not going to cover it. But why I am just going into all these details, because the fourth one is still an open problem. People has proposed something, but you may give it a try. It's still in the research level, that what is the best thing for partially observed data and Bayesian net not given. How can you learn the Bayesian net along with learning some of the partial CPDT, that is conditional table, that is also not given due to partial observability of data. Okay, full observability of data, it is very easy to use a maximum likelihood estimation as we did in the first type of cases and get the CPDT. There only the challenge is Bayesian net, which is not given. But this is typically a very strong problem. So you can go with this, but what people do is they assume something, try to do this one. As we do in the expected maximization, we have two steps, one after another followed. So they assume this, do this one, they assume this, do this one, and they try to converge among them. That they do, but this is still an active area of research. People try to find out. All right. So this is what one of the things that is very much important we need to cover up. Now, yeah.
Sir, can you please redefine the fourth part again? Once, what is the original statement?
Fourth part is Bayesian net is also not given. Your data is partially observable, meaning some of the entries are not there. How can you construct the Bayesian net or learn the Bayesian net, to be more precise, and also learn those CPDTs which cannot be found from directly from the partially observable data?
Okay, thank you,
Both
sir.
things to be.
Okay.
So
now
in
you
the
can.
first formula, we will take all the values for y, right?
This
Like
one.
y, the first, the expectation of y given
Yeah. You will take
x1
all the
x
values of y equal to 1. Yeah, all the
in the
example values.
in the denominator, sir, that y is equals to 1, that y will take the 0 and so on, all the values, right?
Yes,
So,
yes, values. Yes, all the values. Because see here you see now sk equal to 1 and sk equal to 0. Denominator. It's a Bayes theorem.
okay, you haven't
Right?
written that. Okay.
No, I want to mean here G. Yeah, that's a mistake.
Yeah, exactly.
That's a mistake. Yes, it should be J. Yeah, I hope you get the essence.
Okay.
Now see why I covered this expectation minimization not right when I covered the Bayesian, but now is that it has a resemblance with the classification, right? Why? Because if all of the data fields are unknown for the outcome, then isn't it the same as the classification problem or the unsupervised learning problem? Did you get it? See, just try to think in this way. In unsupervised learning problem, you are given with a table, but you do not know the outputs, right? So what if
Yes,
all the
Yes, sir.
outputs are unknown? Then you can apply the same expectation maximization algorithm to cluster. With respect to the probabilities that you get, you cluster it into same probability within threshold, right? So this has a very well applications as well as in terms of finding the unsupervised learning, unsupervised ways, where your output, I will not tell you anything about that. You expect that output to be 1, you expect that output to be 0 and make it into 2 clusters. What is the probability of getting some points into some cluster? Whichever is wins, you put it into that cluster. Get it?
Yes, sir.
Another thing that you will see here, we talked about sometimes in data, given set of data, sometimes you will figure out that suppose I have some data like this one given. Suppose I have some data like this one given. Suppose I have some data like this one given. Now, if you try to go by clustering, you can see that it's a problem. Either it will do a full, if you go by 3 clustering, sometimes what it will do, one cluster is good. This cluster, it will go this way and this way is the rest. But clustering, since it's an unsupervised technique, it mostly depends upon the origination of the data, how the data being originated. If you look how the data being originated, suppose this may follow a Gaussian distribution to originate. This may follow another Gaussian distribution to originate. I am drawing this concentric circle to understand that it's just like a mountain where your concentric circle becomes, this is the mountain top. It's a Gaussian distribution, so everywhere down the line it's a slope wise you are coming down. It's this kind of a distribution, and you are looking it from a 3D angle. So this one may be also drawn from some other Gaussian distribution. So which means, so to simplify it more, suppose in a 2D line you are taking, you have a certain set of points and like that. Maybe these points are drawn from two Gaussian distributions. Often we call it as a mixture of Gaussian models. In those cases, we need to understand this mixture. Otherwise, whatever way we pull out something, we will be wrong in classifying it or clustering it. Because maybe a point here is dependent, that the drawing of a point here is dependent on both the distributions, this and this, both distributions. It has an impact of existence of this point here. So for this mixture of Gaussian models, the expectation minimization algorithm also applies for partially given thing, where you can see that suppose, so the challenge here is a point P. Obviously, a point P is basically n-dimensional point. That means it has n attributes. So a point P is nothing but a vector of n values. So a point P, since it's a point P could be a mixture of Gaussian models, therefore the probability of point P to be drawn from the mixture of a model will be nothing. But suppose I select my Gaussian models to be the ith one, and what is the probability of drawing that point with respect to the ith Gaussian model? And for all models that I have, if I sum over, so the probability of drawing that point from a mixture of Gaussian model is this formula. Let me come again. This point can be drawn from this and this. Both has an influence of this point to be here. So that means the probability of that point to be drawn from this particular position has been influenced by both Gaussians. Suppose the Gaussian 1 and the Gaussian 2. So with the Gaussian 1, there is a probability of drawing it. The Gaussian 2 will have a probability of drawing it. This one is nothing but doing a mixture. Right?
Yes, sir.
So here, see, the unknown part is which are the Gaussians. Here, the unknown part is to find out for a point, that means a point is observed. Your Gaussian thing that you are selecting is unobserved. So which Gaussian you select is the unobserved part to make out this point. So therefore, your E step, that is the expectation step, there we'll try to find out the expected probability given the nth point. I am writing it bracket n because each of the nth point, let me further have capital N dimensions. Each of the nth point is nothing but a vector of x1 up to x capital N dimension. So I have to find out this, what is the expected value of this point being Gaussian I, Gaussian J, Gaussian K. This is my expectation step. And once I can get this expectation, what I will do, I will try to find out what is the probability of this point to be as a mixture of those Gaussians. Okay. So here to solve this, people usually go by certain assumptions. Some of the assumptions are to make the equations simplified. So one of the assumptions is What people make, first of all, they try to make this probability value of x given z equal to some j distribution. Basically, they do that each of the points followed, each of the directions followed a Gaussian distribution with respect to a mu and a sigma, as you can easily know from the Gaussian distribution thing, and they make it as an independent. So all of these dimension Gaussians are independent and they form this formula. That is one assumption. So it means that x1 up to xn are conditionally independent. The second assumption they try to make in this formulation is that they try to find out that their sigma ji's, they say that these are equal and these are known. So what is the unknown part in getting a point? The unknown part for them is, suppose there are two Gaussians, 0 and 1. Then this is probability of z equal to z. This thing, which is the prior probability of z equal to j. This is the prior into, since it is an independent distribution, n over xi given mu ij and sigma, rather mu ji and sigma. This one is also unknown. So what they do is that they try to find out the point probability, this one as we just discussed, by assuming these two are unknown, prior and the mu ij. So that means their theta value that they are trying to seek will be dependent on mu ji and pi. So these two are assumptions to go for the maximization step. Okay, so let me repeat what we are trying to do. In there will be many cases where the points will follow a mixture distribution. A typical example is a mixture of Gaussian distribution. You can change this, since a Gaussian distributions we are taking this one as the Gaussian distribution to take a point. But you can change your one. But it could be a mixture of something. So the influence of different models on a point need to be understood. To do that, we will follow the same expectation maximization algorithm, where we will see that points are observed, which Gaussian influence them are unobserved variables. So I make the formula as the Gaussian, unobserved Gaussian as z. And in the expectation step, I would like to see which of the Gaussian follow this xn and the initial theta that we start with. We make certain assumptions to go with the maximization step, where we will try to maximize the theta with respect to these parameters, because we assume our sigma to be known. We assume this to be known. It makes life simpler, because now what will happen, just let me complete the derivation, then I will stop the class. Everything is there in the slide. I mean, I'm not writing something, anything new. It's just a hairy kind of a mathematics, but the principle is very simple. So what I am trying to do here is, so let us try to write the Q function. Expected value of z given x theta log likelihood of pxz given theta. That is our M step, as always. Now here you can see that I could write this internal formula as probability of x given z comma theta into probability of z given theta. Why I wrote it in this form? Because now this expression will be transformed as log of probability of x given z theta plus log of probability of z given theta. Now see, what is our theta? I mean, when we consider theta, what are the things that are unknown to us? Theta depends on these two things. Now x given z and theta, this doesn't matter with respect to pi and mu ij, because x matters with respect to z. So x is conditionally independent of theta given z. whereas Z is dependent on this. Now we have two parameters in the M step to maximize. As we know, in while we do stochastic gradient, what we will try to do, we will try to do dd pi, and we will try to do dt mu gi to make both as 0 to maximize. So the first one, if we do, since this term cancels, we only have to maximize with respect to these terms we have. Now you can, so the thing is that this is a maximization problem where we need to make this as 0. Now to make this as 0, here you try to remember, if I have a pi as a prior probability for Z, then this will be dt pi of this expected value of the inside part, probability of Z given theta is, so this is the likelihood part of it. So remember the coin flip when we have 0, 0, 0, 1, 1. So that means the number of times I have pi, it will be summed over the number of times Zn is taking place. And the number of times I fail will also be summed over the number of times Zn is not into my picture, considering two Zn's, either 0 or 1. So this will be our inside part. If you simplify it and just proceed it, the details are there in the slide. Finally, you will get this as your answer. Expected value of Zn. But what is the essence that I would like to make here is that we are trying to find the distribution of a point, and it is dependent on a Gaussian set of Gaussian, maybe Zi, Zz, Zk, all of them are responsible to generate this point. Now, I do not know which one of them are responsible. So for a point x1 to xn given to me and all these z1 to zm given to me, I do not have any clue of them. I have a full clue of what is here. Now what I am trying to do, I am trying to maximize if this is 1, the rest is 0. If this is 1, the rest is 0. I am trying to make an expected value of Z1 to be, I mean, I want to make that if Z1 is actually generating this point, if Zn is actually generating this point, that is the expectation step doing. And then in the next step, when we are trying to maximize the theta, we are trying to maximize the likelihood of this point to occur with respect to the theta. That is our maximization step. So here also in Gaussian mixture models, we use this kind of thing. And secondly, we also update this. And finally, we get a theta at each iterations. We do this two solving and get a theta with respect to mu, gi, and pi. And then proceed again with the expectation step, then minimization step, and again, finally we converge with that. What do we converge? We converge with which of the Gaussians has how much influence to generate this point. Okay, same approach, however, just in a different sort of clustering kind of a thing where we do not know which point is from which cluster. Now see, here if you do a mixture of Gaussian, your clustering will be much easier. If you look into this picture, I exactly know which point has contributions from where. Isn't it? Agreed? The end goal.
Yes, sir.
So therefore, I could cluster them according to this. Okay. So just 1 minute to
Yes,
summarize, we started off with a Bayesian network, full observable data. If everything is given joint probability distribution, our life is simpler. Just need to search and find any value. Instead, it will also be simpler if this table is given with respect to conditional probability distribution, but in reality, you are only given a sample of data, not the full joint probability distribution. Forget about the conditional probability distribution as well. You will just collect this data in terms of medical record. Somebody has tuberculosis, somebody has cancer and all that, but not the full thing. Then their problem is fourfold. One, Bayesian network is known. I need to have fully observed JPDT, but not full set of JPDT, but observed JPDT. How can I learn the CPDT? I say that maximum likelihood is a direct application of this and you can derive that. Then I move to Bayesian network given but the partially observable data. Then I saw, well, this is a little bit of challenge, then directly maximum likelihood cannot be given. However, the contribution of each column being a value or not can also dictate the maximum likelihood. So expectation we compute, then compute the maximization and go on rolling over it until we converge to a local maximum, and found that this could be easily done. Then when we proceed on, we could see that ramification is also there in terms of clustering algorithms, because where the unknown is full output column, the whole thing I do not know. Then we saw that the other two are a little bit tough problems, where there is one algorithm, though it forms a tree structure graph, not a directed acyclic graph, where Bayesian net is not given. So when Bayesian net is not given, it's fully a challenge, because you can easily understand, I do not know the dependency, so there is very less I can do. So it's a higher challenge. And the ultimate is that everything is kind of a void. Bayesian net is also not given, some data are unobservable. Now, looking at this clustering problem, we just extend it a little bit to see that sometimes the clustering problem can also be viewed at how this point is generated. It could be generated from two different cluster models. For example, mixture of Gaussian models, and here the which Gaussian we do not know, but the points we do know. Expectation minimization to expect the Gaussian which we do not know, then find out which of the point probability that we have taken to generate this, and can classify accordingly, cluster accordingly rather. Okay, so this is what is the expected maximization and the Gaussian mixture model for that. Any questions?
Sir,
Yes.
so the last explanation you gave for each Z1, Z2, and so on Zm, we are calculating the expectation of it, and we are taking the last formula we got is the expectation of whole expectations, right? The one, the kind of average.
Yes. No, not on average. I mean, what I'm saying is that it's the contribution of these four expectations that generated this point. Right? So see, ultimately, in this example, we'll clarify it. Suppose this point, this green point, it is generated by this Gaussian as well as this Gaussian. Right? So this could be within a cluster of a set of Gaussians. So mixture, I have defined the mixture function as the sum. See, there are two things you can define in your own. You can define your mixture function, you can define your Gaussian function model. Right? How the point is being generated, I thought it as a simple summation of the points. Right? So it means that in my case, what happens is that suppose in a line, take this one. In my case, since it's a summation, so it is like this. Right? Here it will be more, and here it will be absolutely close to this line, and suddenly it will be like this, the distribution. Since it's a sum. Right?
Yes, sir.
Suppose there are two Gaussians like this. How do you make a sum of them? The sum of them is that here there is no influence until I come up in this point, there is no influence. So suddenly here I get a little influence, here is a more influence, here I have a little influence of the other, and then again the same. So this is the distribution through which I generated my points. Get it?
Yes, sir. Yes, sir.
That's the sum factor. Any other questions? Okay, sorry for being a few minutes after. Yeah, Suhas.
Sir, even if we don't have mixture of Gaussians, we have some other waveform mixed together. This method will work, right?
Yes. Mixture of, see, usually what happens, most of the time, see, the Gaussian thing is most prominent in statistical data gathering. So people try to predict their algorithms through Gaussians. As you know, that Gaussian models are most widely popular in statistical data point generations.
Yes, sir.
But algorithm is irrespective of the model. That's what I said. Mixture could be, you can take your max function as a mixture. I will take the maximum impact of one model. That could be your mixture. Mixture could be, I could get just a normalized data. I mean, not normalized, a uniform distribution rather than Gaussian. You can take it, no issue.
Yes, sir.
Okay, so this is I tried to give some essence about why this kind of things evolve. These computations do not get buried into it because it's not too difficult. It's just look here kind of a thing, because all these probability values, this that brackets make it here. But maximum likelihood, if you follow, most of them are done. All of them are ramifications of taking a derivative, making into zero, and the derivative keeps on growing. And in the slides, it's very clearly, though my handwriting may be a little bit clumsy, but in slides, it is totally worked out. You just go with a slide, take an example, go with it, you can easily do what is happening. Okay, so that's all. Let me stop the recording.